Welcome back to Fun Facts Online. Today we are diving deep into a phenomenon that is rewriting our understanding of planetary evolution. It is a story of cosmic trauma, quantum mechanics, and worlds that defy the laws of density. We are talking about the helium bleed and the atmospheric hydrodynamics of superpuff exoplanets. To understand why this is such a massive deal in astrophysics right now, we first need to look at our own neighborhood. In the solar system, we have a very neat, orderly arrangement of density. We have the rocky inner worlds, like Earth and Mars, which are dense and compact. Then we have the gas giants, Jupiter and Saturn, which are massive enough to crush their interiors into metallic oceans. For a long time, we thought this was the rulebook. Dense rocks close in, massive gas giants further out. But then we started finding the superpuffs. These are worlds discovered by missions like Kepler and TESS that completely break our physical intuition. Imagine a planet with a radius the size of Jupiter, but a mass only a few times that of Earth. If you calculate the density, it is not like rock, which is around 5 grams per cc. It is not even like water at 1 gram. These worlds are less dense than cork. They are less dense than styrofoam. They are comparable to cotton candy. For years, this was a paradox. How does a planet with the weak gravity of a super-Earth hold onto an atmosphere puffed up to the size of a gas giant? Why hasn't the radiation from their host star stripped them bare? The answer, as we have recently discovered, is that the star is stripping them. We are just catching them in the act. They are bleeding their atmospheres into the void in vast comet-like tails. This is the helium bleed. Let us get into the physics of how this happens, because it is not just simple evaporation. On Earth, our atmosphere is in hydrostatic equilibrium. Gravity pulls down, pressure pushes up, and they balance out. We lose a tiny bit of gas to space, but it is a slow trickle called Jean's escape. Superpuffs operate in a completely different regime, called hydrodynamic escape. These planets often orbit very close to young, active stars that blast them with extreme ultraviolet and X-ray radiation. This energy penetrates deep into the upper atmosphere and heats the gas to 10,000 Kelvin or more. At that temperature, hydrostatic equilibrium collapses. The thermal pressure becomes so intense that it overcomes the planet's weak gravity. The atmosphere does not just evaporate particle by particle, it flows. It behaves like a fluid, expanding outward in a continuous, supersonic wind. This is modeled using the Parker wind mechanism, the same physics Eugene Parker used to describe the solar wind in the 1950s. As this gas expands, it accelerates. It hits a specific altitude called the sonic point, where the outflow velocity breaks the speed of sound. Beyond that lies the Bondi radius, the point of no return where the gas is lost to the planet forever. For a superpuff, because the core is so light and the gas is so hot, the Bondi radius is perilously close to the surface. The planet is effectively boiling off into space, exhaling its own substance in a wind that carries away billions of tons of material every second. It gets even more violent when you consider gravity. Every planet has a Roche lobe, which is the volume of space where its gravity dominates over the star's tides. Because superpuffs are so large and orbit so close to their stars, their atmospheres physically expand until they spill over the edge of this Roche lobe. The star's gravity then grabs this material, stripping it away in a process that is essentially gravitational disembowelment. Now, for a long time, this was just theory. Observing it was a nightmare because the main gas, hydrogen, is hard to see through the interstellar medium. But nature gave us a loophole, a golden ticket known as the metastable helium triplet. This is where quantum mechanics enters the picture. Helium is the second most common element in these atmospheres. When a helium atom gets hit by that extreme X-ray radiation from the star, one of its electrons gets kicked up to a high-energy state. As it falls back down, it can get stuck in a specific quantum trap called the 2,3s triplet state. Selection rules, which are basically traffic laws for electrons, prevent it from dropping back to the ground state easily. So this metastable helium sits in the upper atmosphere, like a loaded spring, for hours or days. Crucially, it absorbs light at a very specific wavelength, 10,830 angstroms, or 1,083 nanometers. This is in the near-infrared. Why is this the golden ticket? 3 reasons. First, infrared light cuts through the interstellar medium. Second, we can see it from the ground. We do not need a space telescope. And third, because this helium only exists in the outflowing wind, it traces the escape perfectly. By measuring the Doppler shift of this line, we can clock the speed of the planetary wind. If we see the light blue shifted, moving toward us at 20 kilometers per second, we are directly measuring the planet's atmosphere blowing toward our telescope. This technique brings us to the celebrity of the bleeding worlds, WASP-107b. Discovered in 2017, this planet is the Rosetta Stone for atmospheric escape. It is the size of Jupiter, but has only 10% of Jupiter's mass. It is incredibly fluffy. In 2018, astronomers detected a massive helium signal, revealing that WASP-107b is dragging a colossal tail of gas behind it, extending for tens of planetary radii, shaped by the radiation pressure of its star, just like a comet's tail. We calculate that WASP-107b is losing up to 4% of its total mass every billion years. It is actively shrinking. But the story of WASP-107b got even stranger in May 2024. The James Webb Space Telescope looked at its atmosphere and found a mystery. At the planet's temperature of around 740 Kelvin, we expected to see plenty of methane. Carbon loves to bond with hydrogen to form methane at these temperatures. But Webb found almost none. Methane was depleted by a factor of 1,000. Instead, the carbon was in carbon monoxide and carbon dioxide. This chemical imbalance told us something profound about the planet's interior. The lack of methane implies that the interior is much hotter than we thought. This heat drives vigorous vertical mixing, dragging methane-depleted gas from the deep hot layers up to the surface faster than it can cool down and chemically reform. But what is heating the core? The answer solves the whole paradox. WASP-107b has a slightly eccentric orbit. As it swings around its star, the changing gravitational forces knead the planet like a ball of dough. This tidal heating pumps massive amounts of energy into the core. This heat does two things. First, it drives the mixing that destroys the methane. Second, it inflates the atmosphere like a hot air balloon, explaining why the planet is so huge despite its low mass. WASP-107b is a tidally tortured engine, puffing itself up while simultaneously bleeding into the void. Now let's contrast this with the Kepler-51 system. This system hosts 3 superpuffs, including Kepler-51d, which is the size of Saturn but has the mass of a few Earths. Its density is below 0.1 grams per cc. If you had a bathtub big enough, this planet would float high on the water like a beach ball. When we looked at Kepler-51 with Hubble, we expected to see clear chemical signatures. Instead, we saw a flat line. A flat spectrum usually means clouds or haze. This led to the Great Dust Cover-Up theory. Maybe these planets aren't actually that big. Maybe they are smaller planets surrounded by a high-altitude layer of photochemical smog that blocks the light, tricking us into thinking the planet is bigger than it is. It is like a planet wearing a puffy jacket. However, recent hydrodynamic models suggest that to keep dust or haze lofted that high against gravity, you need a powerful outward flow of gas. The haze isn't just sitting there, it is being carried upward by the helium bleed itself. The outflowing wind acts like a conveyor belt. So even if the puffy jacket theory is true, it requires the hydrodynamic escape mechanism to sustain it. All of this brings us to the big picture. Why do we care about puffy, dying planets? Because they are the missing link in planetary evolution. When we look at the census of small planets, we see a feature called the Fulton Gap, or the Radius Valley. We see lots of super-Earths and lots of sub-Neptunes, but very few planets in between. This valley is the scar left by atmospheric escape. The prevailing theory is that many planets are born as sub-Neptunes, basically baby superpuffs with rocky cores and thick hydrogen envelopes. If they are too close to the star, the helium bleed kicks in. The photoevaporation strips the entire envelope away, leaving behind the naked, rocky core, which we then call a super-Earth. Superpuffs like Kepler-51 are simply teenage planets caught in this transition. They are less than 500 million years old. They haven't finished shrinking yet. Over the next billion years, they will likely bleed away much of their bulk. We are witnessing planetary metamorphosis in real time. We are now entering a golden age for this research. JWST is using its NIR spec instrument to detect that helium line with incredible sensitivity, and its MIRI instrument is probing the chemicals in the escaping winds. Ground-based instruments like SPIROU and CARMENES are building 3D velocity maps of these winds, effectively giving us a Doppler weather map of a planet dying light years away. The ultimate question is whether we are seeing the exception or the rule. It is possible that Earth itself once had a primordial hydrogen atmosphere that bled away in the solar system's violent youth. By studying the superpuffs, we are looking into a mirror of the deep past, watching the hydrodynamic sculpting processes that carve habitable worlds out of the chaotic raw material of the nebula. The helium bleed is not just a story of destruction, it is a story of genesis. It is the process that refines the galaxy, stripping away the excess to reveal the rocky gems hidden beneath. Thanks for listening to this deep dive on G Fun Facts Online.